A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Today we are going to talk about silicon quantum dots. We have already discussed the quantum dots in detail, which are a zero-dimensional type of systems and have very interesting application. So we are specifically discussing silicon quantum dot in today's lecture. So this is a part of nanophysics and technology course, which have the course code of PHY445. In today's lecture we will basically discuss the history of silicon quantum dot, how it has been introduced, and the development, how it was made, the development, stage-wise development in the history of silicon quantum dots, the property of silicon quantum dots grown by ion implantation and annealing process, and finally we will discuss the advantages and disadvantages of this particular method. Similarly, we need to discuss some other methods to grow the silicon quantum dots. So, and at the end we need to compare the different methods which are used for this particular quantum dot. So the first thing we need to know is the history of silicon quantum dots. In general, if we consider the history of quantum dots, then the first quantum size effect was seen in semiconductor nanocrystal, and that occurred in 1960s. In general, initially people know about semiconductor nanocrystal, and then due to its interesting application or interesting properties, scientists were trying to develop the quantum dot of particular elements. So that is actually the that also lead to the development of quantum dot of silicon. So initially in 1960 was the quantum size effect was found, that the properties of a material at quantum size are drastically changed from its bulk size, and that was in 1960. Furthermore, in 1970s, Bruce was working in Bell Laboratories, and that were that were working on collider synthesis. Further development were made when some first semiconductor quantum dot were grown in 1980s, and in 1990s first visible photoluminescence scenes from silicon quantum dots. In the visible regime, photoluminescence has been observed from silicon quantum dot in 1990. So moreover, next development has been made in 1993, where silicon optoelectronic integrated circuit is suggested. I mean, we can use the silicon quantum dot in silicon optoelectronic integrated circuit. Furthermore, in 1993, silicon quantum dot have been extensively investigated because of its wide range of application. Different method has been developed to fabricate the silicon quantum dot, just like microwave plasma decomposition of SiH4, laser breakdown of SiH4, plasma enhanced chemical vapor deposition method, high frequency discharge method, and high dose ion implantation method were utilized to prepare these silicon quantum dots. So how the silicon quantum dots are formed? Today we are going to discuss the ion implantation and annealing method. That is actually the basic method what is used for the development of silicon quantum dots. So in this case we have ion implantation, and when ions are implanted and segregated, there are different the stages are followed. Initially these SiO2 ions, Si ions are implanted, and so just like Si we have SiO2, so there is a supersaturation, and later on we have segregation nucleation process, which change the size of these particular elements, these particular systems. So aggregation, growth, and characterization process occurs in the next steps, and finally After the host-wall ripening, the coil says we are moving toward the annealing process, which is the a step toward the formation of silicon quantum dots. So what are the interesting property of this particular quantum dot which make it interesting and utilize it in wide range of application? It is widely used. One of the most important property of this material is the photoluminescence property. That is very interesting, and it has very peak energy and intensity, very high. And the other property, very interesting property, is ranging from its the diameter, the range is from 1 to 10 nanometer, and the size, there is a size distribution within the host material is also possible. So first we need to discuss the photoluminescence property of this particular silicon quantum dots. So this is the curve drawn, or actually this is a PL curves that is drawn between the PL intensity and wavelength of the upcoming wavelength. So we have the absorption peaks for different prepare silicon quantum dot, and then finally we have annealing at different temperatures. So changing the annealing temperature, it can change the peak intensity. Just like here in the right side we can see, when there is the annealing temperature has been increased from 300 to 500, there is gradual increase in the peak intensity. So that is why the absorption capacity has been modified. This is some other curves that has been obtained experimentally, and that also shows the photoluminescence properties. All the curves are regarding the PL intensity versus the photon energy. So it means at which photon energy there will be a huge absorption, leading to the interesting curves. And different silicon quantum dots are, different samples are created with different annealing temperature, and then it is compared which one provide the best value. So here it has been observed in the first case that as we already described in the last case, that increasing the annealing temperature has increased the absorption capacity. The peak intensity has been abruptly increased. Here in this curve, as we again observe that this is the increase in the annealing temperature lead to the increase in the absorption curve, and that is really visible in all particular cases. So it means that the photon energy, it normally the peak is not shifted from one place to another place. If you see the peak here, that lies between 0.5 and 2. Again here in this case is lies in the range of 0.5 to, this is actually 0.5 to 2, coming toward the C. In this case we have, it lies between 0.5 to 2, and in this case again it lies between 0.5 to 2. The peak broadness is remained the same, but only the peak intensity has been increased. So that is why it shows a high intensity peaks. This is some other curves regarding the PL intensity of the same material. The samples are synthesized, the same samples are used, and that's PL intensity is compared with the photon energy, and its variation is changed. So is the annealing time. Here annealing time is used as a parameter to get the sample with optimal properties. So changing the annealing time can change the property of the materials. Here we are looking toward this curve, that we have sample 1, 2, 3, 4, 5, 6 samples which have different annealing temperatures starting from 1 hour till annealing time from 1 hour till 20 hours. So here we can see that initially with the increase in the annealing time from 1 hour till 5 for ABC, for A you see the peak is low, and with the increase in annealing time to 3 there is a gradual increase in the peak intensity that shows the B. And in case of C there is again high peak intensity that is clearly visible in case of C. Moreover, in case of D there is again increase in the peak intensity for 10 hours, and with further increase till 15 hours we found E the peak intensity like this one. And there is a big different effect has been found from E to F, where the annealing time has been increased from 15 to 20 hours, but in this case there is almost no change in the peak intensity. So if we generally interpret, then it will be like that if we keep changing the time from 1 till 15 hours, so there is gradual increase in the PL intensity peaks. But after 15 hours, if we further increase in the annealing time, there is no further increase in the peak intensity and it remains constant. So this is the suggested mechanism for the electron transfer between the gaps, between the bands in these silicon nanoclusters, and how the electron hole pairs are created. Normally when a photon of suitable energy falls on the valence band, so as a result the electron is migrated toward the conduction band, leaving behind a hole. So here in this nanocluster, in silicon nanocluster, would happen when there is an interface is created, and an interface is created between a semiconductor with high band gap and a semiconductor with lower band gap. So a photon move an electron from the valence band toward the conduction band with the help of that particular defect state, and this interaction occurs. So there is a transition of electrons between valence and conduction band. So and there is interaction between the interfacial energy states as well. So this is actually the schematic diagram for the transition of electron between the transition of electron between valence and conduction band, leading to the optical properties of these particular semiconductor materials. So this is another diagram showing the transition of electron. This is actually a two-step transition. One is the electron hole pair creation after the absorption of a particular wavelength, and other is the electron hole pair recombination after the releasing of photons. So in the first case, when a photon of suitable frequency falls on the material, electron is migrated from valence band toward the conduction band. So there are several stops possible for that. Whether the electron can directly come from the conduction band toward meeting the valence band, and the extra the energy is emitted in the form of a photon. This is the first option. The second option is that the migrated electron from the valence band toward the conduction, the migrated electron from the valence band toward the conduction band stay there, and there is maybe some defect state or interface state that is present inside the band gap, and it is migrated or it is perform transition stepwise from conduction to valence band. And in this case, this defect state is used as a step for the transition of electrons. So initially it form a type of thermal transition, or maybe a very short transition from the conduction band to that particular interface state, and later on from this interface state to the conduction band, from this interface state to the valence band, it comes and emit extra energy in the form of photon. The other possible state is the transition of electron between the defect state and the valence band. So that is really interesting, and in this case light is also produced depending on the band gap, or the gap between the defect state and the valence band. So here, when the electron is migrated from the valence band toward the defect state, so after some time, when it come back from the defect state to the valence band, it will emit extra energy in the form of light. So this is one of the possible mechanism that is suggested by this particular scientist regarding this transition of electron between the valence and conduction band, between the valence and conduction band through the interface, and between the valence and defect state of this particular material. So this is one of the range of the size of this particular material. So I means how we can change the size with the help of prolonged annealing process of these silicon quantum dots. So the size distribution within the host material, how we can have the silicon percentage atomic fraction distribution within the host material, how it is, whether it is uniformly distributed, and this curve shows the fraction of silicon, atomic fractions of the silicon that is distributed in depth, in particular depth that has been mentioned in nanometer, and this various curves has been drawn. And on the right side, the PL intensity is again shown, that show the absorption curve for this particular material. So we have defects within the host material as well. So these defects are in the form of point defect, and the point defect change the property of the material. Here it is very clear that the point defect is a type. Point defects are further divided into several categories. Just like in point defect, we have vacancy, we have substitutional point defect, we have a interstitial defect, we have substitutional interstitial, we have impurity interstitial, we have a type of self interstitial. So these are all possible type of point defects which are possible in this particular case. So what are actually the advantages and disadvantages of this particular method? So it's actually, there is a ease of integration into silicon based microelectronics, that are actually the silicon dot and processor. It has the ability to control the PL intensity and peak energy. Some of the drawbacks, or what you call as a demerit of these materials, is also possible, and which are the large size distribution of the material within the host material. So defects are also present due to the at the end. This is one of the disadvantage as well, that the defects are also present at the end, and then surface damages are also possible in this particular method. Except this particular method what we discussed today, there are also some other methods that are used to fabricate the silicon quantum dots, and that are widely used, but that is not actually the part of today's lecture. So we have microwave plasma decomposition of saline gas, that is also used for this particular case. The laser breakdown of saline gas is also a method that has been utilized for the silicon quantum dot, and the plasma enhanced chemical vapor deposition, what we call as that is also used for this particular processing. High frequency spark discharge method is also used for this preparation, and finally the colloidal method is also utilized. So which one is the best? If you compare the different, which one is the best? So we can see that it depends on you want to use the silicon quantum dot. It means for different type of applications different methods are utilized. Looking toward the applications of the silicon quantum dot, uh, and then the particular method is followed. So if you want to make an optoelectrical integrated circuit, then the plasma enhanced CVD is used and ion implantation method is used. So if you use cool fluorescing silicon quantum dot, then the colliding methods are used. So it means that the particular silicon quantum dot method is used for looking toward the application of that particular silicon quantum dot. So this is something about the silicon quantum dot, is fabrication and its property that make it an excellent material. So thank you very much for now.